function. Its a right continuity is there, and limit x goes to minus infinity, f of x is 0, and limit f of x goes to plus infinity is 1. Okay. So these are the things we have discussed. Right? And we have done the proof of this. So that was the property of the distribution function. Now we'll do some definition, that is so the definition says that just one moment. If there is a Borel function, sorry. So what is a Borel function that we have already defined earlier, right? The Borel function is so Borel function is whose inverse image is also a Borel set. I mean, which takes the inverse image of a Borel set to Borel set. That's it. I mean, yes, X is a random variable. Yeah, so this is the definition of Borel function. F is a Borel function R to R. If F inverse B is a Borel set for any B in BR. So in a sense that you consider a Borel set of the ring space, take that inverse, there will be another Borel set. That's the definition of Borel function. Okay? So this was the definition of a Borel function, that you consider a function, real value function, take a Borel set in the range set. The inverse image of that will also be a Borel set. So, yeah, so this was my explanation. And yeah, so it's a Borel. So if there is a Borel function, if epsilon r to r such that for any Borel set, So, so you see that or we can so we can write it. I would say I will write it a little bit differently. Okay. So because okay, I'll write it in a different way. So I can say because we are writing random variable x. Right? So fx is R to R such that for any model set B belongs to R, probability of x belongs to B. Okay. This is equal to integral over the set B and fx x dx. Then uh, so this is defined as this way. Uh, the next is said to a random variable with absolute continuous distribution. And f of x is called the density of the. You see, so in a sense that it's absolutely continuous distribution and it's called the density. So when x is a random variable is called. So you see the left hand side here is nothing but the distribution, right? So so you know the relation between distribution and density. Well, the continuous random variable. For continuous random variable, that you are very much familiar with this type of this type of expression, right? I mean, between between the density and the distribution function. And, yeah, I mean, what you know is yeah. So in a sense that what you know, I mean, is earlier. I mean, what you have already seen in the probability courses is like this f x of x. is equal to minus infinity to f if x. This is you are familiar for the this is the distribution function, and this is the density function. And yeah, and you see, uh, because so this is the and what we have seen for the this density of the this density distribution function, this definition is uh, is yeah, you see that fxx is equal to nothing but probability of x less than equal to b, right? And we have so this is the thing px b equal to uh, this probability of x belongs to b, right? And this is the this thing probability measure. It induces every random variable gives rise to a probability measure, and that's the way. And from there. And this px is the distribution function, and this is the thing. And so in a sense, for absolutely continuous random variable, uh, so in a sense that if you have a distribution function, then just 1 minute. For here, so what does it imply? It implies that x less than equal to x is equal to minus infinity to x fx x dx, right? Because this is nothing but the by definition fx. So, and so x less than equal to x means omega such that x omega less than equal to x. That means minus infinity to x, and that is what here. And so similarly, if you remember, there is also perhaps continuous random variable. There is a thing that this f prime x is equal to fx. Right? That is, if you do the derivative, then this is the fundamental theorem of calculus. Uh, that gives you the relation between the distribution and the density function. These are well known to you. It is just that in this case you write it with write it in this manner. I mean, it's over the set B. X belongs to B is nothing. The integral over the integration of the density function over the set B. And that's the thing. And fx is the density of the random variable. Now, I mean, now there is a natural question that so in a sense that you see, if you have a distribution function, then it has a density, and you write this is the connection with the this thing, relation between distribution and density. But the question is, does all continuous function, continuous random variable. There's all continuous random variable. Sorry, continuous distribution. Sorry, sir. For the similar question, for the similar question, is it possible to construct some kind of continuous distribution of function that do not have density? You can have the
So all continuous function basically. So because if we look for a continuous function, we have a value at each point. If we look in such a way, then the density is equal to the value it has at each point. And then we have number of all, then it is a continuous distribution.
sorry, repeat.
So likewise, if we draw a graph of a continuous function at each point.
No, I don't understand your question. You repeat again, please. Sorry. Repeat. Please repeat.
Sir,
Yeah.
sir, I was saying like if we draw a graph of a continuous function, we have a value at each point. So likewise, if we see that the density at each point cumulates to the continuous distribution function, then all continuous functions have densities, sir.
All continuous function has densities. Uh, no. Uh, you see that okay, so what is the definition? So mm, let's write the definition of continuous random variable. So a random variable, uh, so x is called continuous, okay, random variable if probability of x is equal to 0. Or, okay, x equal to x for any x in real line. You can write it in this way, or you can write it x belongs to R, whatever. So, for any small x equal to x is equal to 0. So in a sense that I mean x is a continuous random variable if and only. Okay, this is an if and only. If and only. So if and only. Uh, if and only it's if and only distribution function fx, I just write it like is continuous at every x in R. So this is my definition of continuous random. And now you see, Uh, uh, I mean, you can have continuous random variable which does not have density. I mean, uh, you can construct it. I mean, I will say, so, I mean, do you know something actually? No, no, it is actually the point is my answer is it is possible. So in a sense, does all continuous distribution has density? The answer is no. Okay. And if someone asks you, is it possible to construct example of continuous distribution function that does not have density? Is it possible to construct? The answer is yes. It is possible to construct. Yes, it is possible to construct. Uh, how will you do it? How will you do it? Do you people know anything about Cantor set? Do you know anything about the Cantor set?
So these are a set of uncountable numbers that in an interval of 0 to 1 we divide in such a way that 1/3 is removed each time.
Yes, yes, yes.
And we
Yeah, you are correct. You correct. And it's an infinite, so it's a Cantor set, and so Cantor set, and the corresponding is the Cantor distribution. Okay, so corresponding is the Cantor distribution. So Cantor distribution is the example. Cantor distribution is the example which is a continuous distribution. So it's a very pretty intelligent. Is a continuous random variable which does not have a density. You see? So that is what I was wanted to feel by. Probably I'll discuss the Cantor. I'll give a little bit idea of this thing. So yes, it's possible. So does all continuous distribution function has density? The answer is no. Is it possible to construct example of continuous distribution function? that do not have density, the answer is yes. And the perfect example is the Cantor distribution. Okay? Cantor distribution function is which is a continuous random variable and which does not have a density. We'll discuss about it. So so but the main thing which I wanted to say that continuous random variable which has density, they are called absolutely continuous distributions. That is what the definition I started with. So continuous random variable, it is not really have a density function. Okay? You can construct such examples which does not have density function. But a continuous random which does have the density, they are absolutely continuous. So a continuous random variable having density makes it an absolutely continuous distribution. Okay? And yes, yes. Okay, we'll take a 10-15 minutes break, then we'll start. And yeah, probably let me give an idea what is a Cantor set. Does everyone know what is a Cantor set? Hello.
No, sir.
Okay,
We
we
don't know, sir.
yeah, we'll discuss about it. It's a nice example. Okay, we'll discuss about it. But not in that detail. We'll just give a because yeah, it requires a lot of sophisticated mathematical analysis. We will not go that deep, but at least we'll discuss what is it. But the main point I want to know is continuous and variable does not necessarily imply you will have a density. Possible to construct a variable which does not have density, but it has, it's an absolute continuous function. It has its or they are absolutely continuous. I think you know the difference between continuous function and absolute continuous. That you can check. The continuous function, there is a continuous function and there is absolute continuous function. There is a difference that you can check. Okay, we have okay. Okay.
Yes.
Yeah. So yeah, so what we were discussing is that Yeah, so there is a so what is a Cantor set? So first of all, Cantor set is a very interesting example. So